Okay. Let's do a video now on related rates proper. This is following the last video, which at the very end of which I sort of just started talking about relationship equations, relationships between various quantities, which might have some kind of physical interpretation or relevance or meaning toward the real world. And we are going to take those relationship equations and use calculus to get or obtain from those relationships between the rates of changes of the quantities involved in those relationship equations. You'll see what I mean, I hope. But that's the idea behind this whole related rates program. Now, we're going to have a video here right now, but rest assured that there will be plenty of discussion about this in the week following 10/17, when hopefully, unless I die in Southern California or something like that, or something catastrophic should happen, we should all be back to sort of your regular programming and all of that starting on October 21st. Yeah. So I do want to also mention that there is a worksheet about related rates. Here is that worksheet where here. Good. Yeah, here's the worksheet on related rates. It talks a little bit about dimensional analysis, which is a useful sort of gadget for understanding how or the effect of taking a derivative on the units for a particular quantity. And it really just follows the sort of Leibniz rule. Uh, it really follows Leibniz rule, so that if you see something like ds dt, the units on that are going to be units of s per units of t. And that's always a useful thing to know, because you want to make sure that you can check, like you can check the sanity of your calculations by examining them dimensionally. And with that in hand, you can be sort of a little bit more comfortable that what it is that you're doing is actually correct and all of that. Here is where we began, or here's where I began in the worksheet, talking about relationship equations. And you can see I've given here 5 plus 5 plus 1, so 11 different examples of these, and obviously there's a lot more of them. Oh, look, I even write, there are obviously a lot more. Okay, great. And you have the sort of scheme here for how we're going to get at this sort of relationship between rates of change. That's what we're going to call the related rates equation for a particular problem. Let me just, instead of talking about it, let's go to this thing and start actually doing it. These are the examples that I gave you last time of some things. Oh, actually, let me just back up one more time, because I realized that when I was doing some other stuff, and I realized I sort of said something weird, and sort of missed the point in the last in the last video. So I want to just fix that. So yeah, this was the point that I missed. So remember when we were talking about this crazy curve here, and I was saying that you could get at the I believe I made a mistake, because I said you can get at the rate of change in y when x is equal to 1 by looking at this tangent line here. The problem with that is, if we zoom out a little bit more, there's actually, and this is really the point, there's actually two different points whose x coordinate is 1, right? There's also this point down here, 1 comma negative 3. That's a different point altogether, whose x coordinate is still 1. So really what I should have been saying when we had this discussion about, remember we zoomed in on the green curve and the purple line coincided, and so the rate of change of the purple line, which is also known as the slope of the purple line, could be taken to be the rate of change of the green curve. I believe I said the rate of change of the green curve at x equal to 1. But that was inaccurate. That was probably not a good thing to say. Not probably. It wasn't a good thing to say. I should have been more specific, because we have to specify both the x and the y coordinate. It's more accurate to say that 1/4, which is the slope of the purple line, c, is the rate of change of the green curve at 1, 1. Whereas the instantaneous rate of change is going to be some other value at this other point whose x coordinate is 1, namely 1, -3. Okay? All right. So I apologize for that oversight. It's like I undermined everything that I had said. That's the whole point, right? But that sort of thing, it tends to happen. Okay, so anyway, let's get back to the subject at hand. That was an interruption, but that's okay. You know that that's usual fare for me. Okay. Let's imagine, for example, let's take this first example of the relationship between circumference and radius. We know c is equal to 2 pi r, right? Easy, right? That's something that you learned in high school. Let's now imagine that r is a quantity which is changing with time. Okay, so under what circumstances would you have such a situation? Well, you could just imagine a circle whose radius is increasing, or maybe it's decreasing or whatever. You could imagine such a situation, couldn't you? Just a circle which is getting larger in radius and then getting smaller in radius. I could probably model that pretty easily in something like Desmos, right? Like we could do a circle like this. So a circle of radius, why am I doing this? A circle of radius r would be given by this equation here. A circle of radius r, where r is the radius, and again, centered at 0, 0. Sorry, my brain is all over the place. It's clear. And you could imagine r growing, and you can imagine r shrinking. You could imagine all sorts of different things, and we get circles of different radii. Okay? Now, if we prescribe carefully the way in which r is changing, the rate at which r is changing with time, so that is to say, if I tell you what dr dt is, if I tell you what dr dt is, perhaps we can get a handle on how the area of this circle is changing. Do you see what I'm saying? So you could imagine, for example, instead of r being here, what if r was some kind of function of t? Like, I don't know. What if it was, let's make it be sine of t plus 1 or something like that. You could imagine. And what we could do is animate this so that what's going to happen is that what's going to happen here is that the radius is going to sort of oscillate between in this case 1 and 2. At least I think so. Let's just see what happens if I animate this. You can. I guess sometimes the radius is 0, huh? So the radius actually oscillates between 0 and 2. Can I make it go slower? This is like hurting my feelings. Well, whatever. You get the point, right? Is that if we make the radius of this circle change with time, then the circumference of this circle is going to also change with time, as will various other aspects of the circle that we may be interested in. For example, its area. And so what we would like to know is that if we have some kind of precise expression for how the radius is changing, can we somehow obtain a nice description of how the area is changing or how the circumference is changing? That's the game with related rates, at least as far as this particular example is concerned. So imagine, please, that r is a quantity which depends on time. Then evidently c is also going to depend on time. But because c is equal to 2 pi r, okay, what we could do to find such a relationship is take d dt of both sides. And what we end up with is what we might call, or what I'm going to be calling, the related rates equation. Okay, so what I could do with C, so with this example right here, what I could do is start with C equals 2 pi r, and now d dt both sides. Why d dt? Because I'm imagining that r is going to be changing with time. Time, did you know the first letter of the word time is t, which is why I'm using t here as the thing that I'm taking the derivative with respect to. Okay, so if I take the derivative of c with respect to t, what I get is dc dt, which is naturally interpreted as the way in which circumference is changing as a function of time. And if I apply d dt to the other side, I get d dt of 2 pi r. Now, what's d dt of 2 pi r? Well, I can take this 2 pi and I can export it outside of the derivative. That's by the constant multiple rule, right? We know that constant multiples, we sort of we can take them outside of the derivative, take the derivative of what's left over after we get rid of the constant multiple, take that derivative and put the constant multiple back in. So in the end, what we get here is dc dt is equal to 2 pi dr dt. So this is what I would call the related rates equation. That relates the rate of change of the radius with the rate of change of the circumference. Okay? Let's do the same game now for the area. Okay, so start with a equals pi r squared. Take d dt of both sides of a equals pi r squared. So on the left, that's the left, we get dA dt. And on the right hand side, again by the, well, maybe I'll write it out, d dt of pi r squared. Well, again, by the constant multiple rule, we can export the pi, swap the pi and the d dt. So this is pi times d dt of r squared. Okay. And now what are we going to do to attack and kill this derivative, or to rewrite this derivative? We are going to use the chain rule, right? To take d dt of r squared in this case, what we're going to do is first take the derivative with respect to r, then multiply by dr dt. So another way of writing all that is to say that this is pi times ddr of r squared times dr dt. It's like the dr's cancel one another, right? It's good. And ddr of r squared, we know what that is. That's 2 pi r. So cleaning all this up, we get the related rates equation. dA dt is equal to, well, it's, so this is going to be 2r right here. This piece right here is 2r, right? So I have to put the 2 in front of the pi. You just have, okay, 2 pi r dr dt. Okay. Yeah. So this is a related, I'd also call this a related rates equation. It relates the rates of change of two different quantities, the radius and the area of this circle. Okay? Or the area enclosed by the circle, whatever. How about this one? Hypotenuse. What does the related rates equation look like here? That is to say, what does dc dt look like in terms of a, b, dab, da dt, db dt? It seems like I'm saying a lot of letters in a row because I am, but hopefully they mean something. I'll say it again, how does dc dt, the rate at which c is changing, relate to the rate of change or rates of change of a and b? Well, we can find out by doing what we did up above. We just take d dt of both sides of that equation, of this equation. I don't know, yeah, of c squared equals a squared plus b squared, under the assumption, of course, that all of these quantities are time-dependent quantities, meaning that they are themselves dependent on time in some form or fashion, right? If we take d dt of both sides of this, okay, I'll go slow. It's d dt of c squared is equal to d dt of a squared plus b squared, right? Now we have to massage both sides of this, you see. So we get that 2c dc dt. Oh, that's the chain rule. Did you know that the chain rule just happened right there? Why? Because I first take the derivative with respect to c to get 2c, then adjust my answer by dc dt. Does that make sense? I'm going a little bit faster because I'm expecting that we are getting more comfy with that. 2a dA dt plus 2b dB dt. I used the sum rule there and I didn't say it out loud, but I'm hoping that you understand. So how does the hypotenuse change? Well, here is the related rates equation. And, oh, maybe I should comment a little bit on these things. There's kind of an interesting thing happening here. Like, look at this first one. This had, oh, and this C, please, okay, is not the same as that C. That's a capital C. I know it looks exactly like a lowercase c. Well, it's not exactly, but anyway, that's a capital C. That stands for circumference of the circle. That's related to this example right here, okay? I guess that's important to know what all the letters mean. Yeah. What am I saying? Right. So look here. Do you see that dc dt depends only on dr dt? Okay. In other words, the only thing that I need to think about, the only question I need to ask when I'm asking about dc dt is how is dr dt, or what is dr dt? What is happening with the radius? If I know the rate of change of the radius, then I know the rate of change of the circumference. Okay? That's not the case with the area. I need to know more in order to understand the rate of change of the area. I do need to know the rate of change of the radius, of course. There's a huge difference between dA dt if in dA dt if dr dt is 5 meters per second versus 15 meters per second, right? There's going to be a large difference in the value of dA dt that we want to make sure that we're keeping track of. But another thing that we need to know is what the actual radius of the circle is at a particular moment. That's made evident by the fact that that r term appears in the related rates equation in this related rates equation. Yeah? Okay. And you can see even something more complicated down here. In order to understand how the hypotenuse C of the right triangle is related to the other two sides, you need to know not just a dA dt and dB dt, you also need to know A and B, okay? And by the way, you also, I guess, need to know C. But do you really, I mean, you could actually rewrite C, couldn't you, in terms of A and B? I think so, right? That's what Pythagoras' theorem sort of supplies for us. Okay? And in fact, Pythagoras, I guess, is giving us this equation here. So, whatever. You would want to know, in particular, C, A, B, dA dt, and dB dt. And you'd put all that together, and that would allow you to compute dC dt. Okay, let's do one more. Let's do this last one, the surface area, and then we'll get to doing some actual problems, related rates problem. Let's do this down here. So d dt both sides as usual. I'm going to get ds dt on the left, and on the right, I'm going to get d dt of 2 pi r squared plus 2 pi r h. Now, this is admittedly more complicated, right? Okay. d dt of 2 pi r squared. Okay. We did something very similar with d dt of pi r squared. We know how to do that. We just take the 2 pi out and take d dt of r squared. That gives us, oh, and how do we take d dt of r squared? Chain rule. We first take ddr of r squared to get 2r, then multiply by dr dt. Okay, that's the derivative of that first piece. The second piece is a bit more complicated, so let's be careful with it. I'm going to go slower. 2 d dt of 2 pi r times h. All right. We need... Oh, maybe, yeah, this is a good moment. I'm saying this requires special care, that it requires some kind of gadget that we've learned about already. What is that gadget? I'll give you a hint. Two-word phrase. The fourth letter of the first word of this two-word phrase is D. Does that help? Pause the video and figure it out. Okay, did you figure it out? Is the product rule? Yeah, of course. Because after all, this is a product of two quantities, r and h, which could be changing with time. So we have to use the product rule in order to evaluate the derivative with respect to t of that product. So I'm going to clean this part up because that can be simplified to 4 pi r dr dt. This 2 pi goes outside of the derivative. And then we take the derivative of r times h with respect to t. And by the product rule, that's the derivative of the first piece, which is, by the way, dr dt, times h, that's the second piece left alone, plus r times dh dt. That's the first piece left alone times the derivative of the second. Okay? All right. And I guess we could distribute the 2 pi in. I'm not too worried about that. I'm just going to box this for now. And I'm going to say this is our related rates equation for the surface area. In order to understand how the surface area is changing, and yeah, in order to understand how the surface area is changing, we need to know lots of stuff. We need to know r, we need to know the radius, we need to know dr dt, we need to also know h and dh dt. So we need to know the rates of changes of it, like all this stuff, yeah? Okay. That's the game for finding what we're going to be calling the related rates equation from the relationship equation. The basic process is that you start with a relationship equation, and essentially you get to a related rates equation by taking ddt of both sides. That's typically how that's going to be done. All right. Okay, so what's an example of the sort of problem which we might encounter for which something like this is useful? Well, let's look at this window here again. So 13.2 is a nice 13.2, 13.3, and 13.4 give you practice in computing related rates equations from relationship equations. So you should try those. I give you an example here for area. Yeah, that's worded weirdly by me. Maybe I'll fix that someday. 13.3 has to do with the area of a rectangle, which you know is the product of the side lengths, x times y, if you call x one of the side lengths and y the other side length. So this asks you to find dA dt, which is going to be in terms of x, y, dx dt, and dy dt. And it says, note that you have to use the product rule. Okay? And finally, here's a problem involved in circuits and such. This is whatever, whatever this is. Okay, this equation here, which is useful in circuits, would be you want to find a related rates equation relating the rates of change of RT, R1, and R2. Then if we move on, I give you an example. Let's look right here at this example of a related rates problem. And I'll write it down, but I go through this explanation here. You can follow along in the worksheet if you like, but I highly suggest, again, that you take notes. Let's do this problem. So example problem. I'm going to tell you that the radius of a sphere is increasing at 2 centimeters per minute. At what rate is the volume of the sphere changing when the radius is 5 centimeters? Okay. Okay. I've been in the game long enough to know how you feel about what just happened. You groaned, or not all of you, but the average of you has just groaned inside because this is what we call a word problem. And even though you all as math students are constantly exhorting your math instructors to tell them, when is this applicable? What is the relevance to the real world of this or that technique? Which, by the way, makes some of the less charitable or the sort of less patient among us math instructors, that makes us groan. Because you should just want to learn this for its own intrinsic interest. Should doing a lot of being a very whatever. I don't know why I'm going down this road. You're groaning because this is a word problem and you don't like words in math. You don't like it when there are letters at all in your math. You would rather just be doing problems like 5 times 5. There's no letters in there. Now there's like way too many letters, because now you have to actually interpret what this is saying in English and take the steps to translate these words into the language of mathematics. And that's never easy, okay? We have to build up our skills to do that effectively. But I insist that it's the kind of thing that you can do. First thing, let's establish well, maybe the very, very first thing that we should do is just decompose this problem into phrases and try to translate those individual phrases into mathematical statements. So the way that I'm going to set this up at the beginning is say the following. Let's define some variables, okay? For example, let's call V, and I don't know why, but I'm going to make it be the capital V. Let's define this to be the volume of the sphere. Why did I choose V? Did I have to choose V? No, but I chose V because V is the first letter of the word volume. That's why I chose it. Let's let R be the radius of the sphere. You can probably see that this is going to be a relevant quantity. R is the first letter of the word sphere. No, it's the first letter of the word radius. It's the second to last letter of the word sphere. Both of those are equally good reasons to choose R to stand for the radius of the sphere. Maybe one's better than the other. And finally, I'll just write this down, but this is going to be very typical. T is going to be the time here. It's going to be time, okay? It might also be useful to keep track dimensionally of the units involved here. So, for example, the unit of length in this problem is centimeters, right? So I might indicate that by saying this radius, which we know is going to have units of length, is going to be measured in centimeters. I would indicate that personally like this, with square brackets writing centimeters. Time is going to be evidently measured in minutes. That's sort of handed to me in the problem. So I'll just write that. If I really desperately wanted to know the answer in terms of some other kind of unit per some other kind of units, I would have to do the conversion. But I'm not so worried about that right now. This is fine. And by the way, what it then is going to be the volume of the sphere, the units on the volume of the sphere. Well, that would be cubic centimeters. So centimeters cubed, which you might, yeah, you could write it like that. Cubic centimeters. I think maybe people sometimes write CCM or something like that. I don't know. I don't understand that stuff. Okay, so anyways, this is fine. Good enough. All right. Now, let's look at these. Let's decompose these words into pieces. For example, I want to look at in red here this first statement. The radius of a sphere is increasing at 2 centimeters per minute. Now we need to translate that statement into a mathematical statement, into a mathematical equation in particular. So let me write that down. I'm going to write all this down. I'm being very, very meticulous at in this first problem here. I will be less meticulous later. So I'll put this in quotes. This is a portion, a phrase, a sentence that I've ripped out from the problem statement. And what I want to do is translate it into mathematical jargon. Well, what we know is that this is saying something about how the radius, which we call r, by the way, see, look, saying something about how r is changing with time. So that is going to be encoded by the quantity dr dt. Remember me saying that this is the most important interpretation of the derivative and probably the most important fact or concept that you're going to be getting out of this course, which is that the derivative of something like dr dt encodes for you the way in which, in this case, the radius r is changing with time t. Okay, dr dt is increasing at 2 centimeters per minute. So what that's saying is that dr dt is equal to 2 centimeters per minute. That's the translation of this English phrase into mathematics. Okay, and that's going to be important and useful for us in just a moment. Then we have this statement: at what rate is the volume of the sphere changing? Let's just focus on that green part. At what rate is the volume of the sphere and I'll put a dot because the sentence continues on. So this is part of the first part of the question. What is it asking for? It's asking for, I guess I should, the volume's here, changing. I should put that changing word because that's key. What is it asking for? It's asking for dv dt, right? This is sort of translated to the fact that we want dv dt. I want is not a mathematical thing, but that is what we want. So this is, I guess, kind of me translating that bit into mathematics. And then finally, changing when the radius is 5 centimeters. If I had another color, I would use it, but I just have black. Changing. Sorry, I messed this all up. When the radius is 5 centimeters. It's fine. Nothing is catastrophically going bad, but yeah. When the radius is 5 centimeters. ... How do we say that? That we want this when r, which is the fifth letter of the word sphere, is 5 centimeters. The radius is 5 centimeters. Okay? Okay, great. So what we can do with all of this is try to, well, solve this problem. We've translated a bunch of information. How are we going to do this? So let's do that kind of over here. So first, let's find a relationship equation. And we typically try to find a relationship equation, not with the variable time. We typically try to find a relationship between the other quantities. And here you really just have to know a formula. Maybe you learned it in high school. Maybe you never learned it. Here it is. The relationship between the volume of a sphere and its radius is 4/3 pi r cubed. V is equal to 4/3 pi r cubed. This is a relationship between V and R. Yeah? Great. Now, where did that come from? That came from my head. How do I know it? Because I've proved it. When did I prove it? I don't remember. Maybe in Calc 3? Maybe when you learn about multivariable calculus. You get no, you can even learn this in Calculus 2. This will come out of some stuff that you can do in Calculus 2 even. So yeah, you will learn this fact, or the reason why this fact is true, again, next semester, if assuming you make it that far. Okay, so that's the relationship equation. Once you establish that, now do what we did on this page. Go from the relationship equation to the related rates equation by taking d dt of both sides. Okay, d dt both sides. So if we d dt the left, we get dv dt. And if we d dt the right, 4/3 pi is just a dumbass constant. So we get 4/3 pi times d dt of r cubed. And as usual, I'll go a little bit slower because I don't mind. 4/3, that's the same thing as ddr of r cubed times dr dt. Easy to write because it's like the dr's cancel, as I've said many times now. But this has the virtue of making this part right here easy to compute. That's just 3r squared. So I'll rewrite dv dt here, and then we get, and the 3 that comes down by the power rule from r cubed kills and is killed by the 3 in the denominator there. So we get 4 pi r squared dr dt. And I boxed that just because this is an important moment in the problem, because this represents the related rates equation. Now, there are a couple things that I really want to emphasize here, okay? Look at the problem statement. Here's going to be the number one issue for students when you are doing this problem. I've taught enough of this stuff that I know where the pitfall is. Here's the pitfall. You read this statement and you're like, oh, the radius is 5 centimeters. Therefore, I'm going to plug 5 in for r, because the volume when the radius is 5 centimeters is 4/3 pi times 5 cubed. You are not wrong. None of what you said there was wrong. But what happens is you then take d dt of both sides of that equation at the particular moment when r is 5, and then you're just totally off the rails because you're just seeing constants in front of you. It all just falls apart after that. This r equals 5 centimeters represents a particular moment in time, or a particular moment for the radius. And what we don't want to do is plug that in prematurely, because we need to know, or we need to understand how the radius is sort of changing No, so like knowing r is 5 centimeters is cool, but we want to somehow combine that with the information about how r is changing with time. We want to somehow get dr dt equaling 2 into the mix. In other words, we want some kind of related rates equation so as to be able to get at what dv dt is. I hope I'm making sense and that's clear. What am I saying? Bottom line, don't plug in things prematurely. I know you see here r is equal to 5. Don't plug that in to your relationship equation prematurely unless you know what you're doing. And don't do it before you obtain the related rates equation. Once you get the related rates equation, that's when you should feel comfortable plugging in information about the moment you care about. And that's actually the third step here. So we're going to plug in particular, dr dt, which is equal to 2 centimeters per minute. I'll just leave off the units. And r is 5. Actually, can I just say something about units? Remember, this has units of centimeters. This has units of centimeters per minute. And I want you to see how this equation here dimensionally makes sense. Or frankly, let's look up here even. This equation dimensionally makes sense. Why? Because what are the units on r again? Centimeters. And what are centimeters cubed? Those are exactly the units on the volume. 4/3 pi have no units. They're what are called dimensionless quantities, right? And so they don't do anything to the units here. But now look at dv dt for a moment. dv dt, okay, what are the units on those? That's going to be cubic centimeters per minute, right? Cubic centimeters per minute, because we're measuring how the volume is changing with time. What are the units on r squared? Centimeters squared. What are the units on dr dt? Centimeters per minute. So what are the units on the product? Centimeters cubed per minute. So you can see how dimensionally, unit-wise, this equation, this related rates equation, makes sense. It is in compliance. Okay, that's a good thing to check and observe. That's why that sort of analysis is why I want you to sort of have a handle on the dimensional, on the units that are involved here. And it's not just because your chemistry and physics and your other instructors might yell at you. I don't care if they yell at you. That's fine, because that has nothing to do with me. But they might yell at me, and then that's a problem, right? Because maybe you don't know about dimensional analysis as well as you should. Anyway, let's plug this information into the related rates equation. If we do that, we get that dv dt at the moment we care about is 4 pi times 2. I'll leave off. No, I'm sorry, 5 squared. Times dr dt, which is 2. 5 squared is 25. 25 times 2 is 50. 50 times 4 is 200. So we get 200 pi centimeters cubed per minute. That's the answer. What did we want? We wanted dv dt. When did we want it? When r was 5 centimeters. How is r changing? At 2 centimeters per minute. We took all of that information together with the related rates equation to come up with this number. Okay. Let's do another one. This is a classic problem. A 13-foot ladder is leaning against the wall. Oh my God, there's so many letters to write. Okay, I'm sorry. Is leaning against the wall. The wall is straight and perpendicular to the ground, as many walls are. The top of the ladder slips down the wall. At 2 feet per second. How fast will the bottom of the ladder be moving away from the wall? Oh my goodness. When the top is 5 feet above the ground. Question mark. Well, I'm going to go fast because I've got 5 minutes. No, I've got 4.5 minutes in principle here. The way that I'm going to do this problem is to begin by drawing a picture of the situation. Here's the wall, there's the ground, and here's the ladder. Now, I don't know about you, but I see a right triangle in this picture, okay? And what I know here is I know some things about this right triangle. I might call this thing here H to stand for height. This thing here, I don't know, call that X to represent the distance between the wall and the bottom of the ladder. And I could give a variable name to the length of the ladder. Maybe I call it L, because L is the first letter of the word ladder. It's also the first letter of the word length, interestingly, but that's not why I'm doing I'm not calling it L for that reason. Point I want to make is that L is not changing with time. The length of the ladder is fixed in this problem. So it's not worthwhile for me to give it its own name. You could. I'm not saying that it's wrong to do that. All I'm saying instead is that you don't have to. You can just replace it by what its value is, 13 feet in this case, and that's fine. And that's what I'm going to do. You can investigate what happens if you don't do that in the course of this problem. Now, we are being told that the top of the ladder is slipping down the wall. You can imagine that. So that's a statement about the rate of change of h. What that tells us is that dh dt, okay, the rate of change of h, that h is in fact shrinking. It's getting smaller, right? So that the derivative dh dt is in fact negative 2 feet per second. Every second that passes by, the height decreases by 2 feet, which is the same thing as saying that it changes by negative 2 feet per second. I hope that makes sense. And what we want, it's always good to know what we want. We want dx dt, how fast the bottom of the ladder is moving when h is 5. Okay, I have 2 minutes. How do we do this? We first find the relationship equation. Find the relationship between these quantities here. Now, I won't leave you in suspense. There's a really good relationship equation, namely the Pythagorean theorem. We know that the sum of the squares of x and h is exactly the square of the hypotenuse. The hypotenuse here is 13. Did you know 13 squared is 169? Great. That's the relationship equation. This relates x and h to one another. All right? 2, d dt both sides. The derivative of x squared with respect to t is 2x dx dt. If you don't understand why that is, chain rule. If you didn't understand that, or that that's not a sufficient explanation, go back to when we were talking about the going from relationship equations to related rates equations. And h squared is 2h dh dt. And that's equal to d dt of 169. By the way, that's 0. Because it's a constant. All right? So, now this is the related rates equation. And we are prepared now to shove information into this. What information do we know about the moment we care about? We know dH/dt, it's -2. We even know h at the moment we care about. H is 5 feet at the moment we care about. This is the thing that we're hunting for, dx/dt. So what is left over that we still need to know? That's x. How do we find x? Well, we can go back here. Okay, so at the moment we care about, let me record some information. I'm going to go a little bit over, and you're just going to have to deal with that. At the moment we care about, h is 5. dH/dt is -2. This is me just rewriting the material information we've been given. We need to know x at the moment we care about, but we can obtain that by solving this equation. We can find x at the moment we care about by solving this equation, x squared plus h squared equals 169. So if we plug in h equal to 5, we get that x squared plus 25, that's 5 squared, is equal to 169. Nice. And then we can subtract 25 from both sides. And then we can take the square root of both sides. Okay. Now, one of these, obviously, we can ignore. We can ignore the -12 because x, after all, is a length. It's a length between the bottom of the wall and the bottom of the ladder. Okay, so we can ignore x equal to 12. So -12. So therefore, at the moment we care about, x is 12. X is a length, so x is equal to 12. Great. Now we can plug in all of this information into the related rates equation. I'm going fast because I'm out of time. We're going to plug all this information in. And so what we obtain is that 2 times 12 times dx dt, and dx dt is the thing we're hunting for, plus 2 times, what was h again? 5 times dH dt. And what was dH dt? It was -2. But this was all equal to 0. Okay? -2 times 10 is -20, but I can move that over to the other side to get 20 and then divide by 24. So dx dt is equal to 20 over 24, which is 5 sixths. 5 sixths. 5 sixths. 5 sixths. 5 sixths units of x per unit of t. So what are the units again? Units of x are feet. Units of t are seconds. So this is feet per second. Okay, I'm done now. These problems get harder. They get much harder. These two problems here are relatively easy ones. So if you don't understand these, make sure you go through these videos very, very carefully. We will talk about the more complicated ones together in class, and you'll have plenty of opportunities to ask questions. But in the meantime, you should be able to do at least a few of your homework assignment problems that relate to related rates. And if you're feeling saucy or adventurous, you can attempt some of the other ones. You have, in principle, all of the tools that you need. It's just putting all of those things together, I know, is not the easiest task for students. But do your best. All right. Have a great rest of your week, and I will see you someday, let's hope. Okay, bye.